Bueno, buenas tardes a todos. Disculpen todos los inconvenientes. Se había colgado la compu, parecía que no había internet, bueno, todo junto. Pero bueno, ahora sí vamos a empezar. Voy a presentar al doctor Xianming Han, que es un visitante que tenemos en el IAFE por estas 2 semanas que siguen. Y bueno, si bien ya había más o menos un resumen de su CV en la publicidad que enviamos a todos, les cuento rapidito. Él realizó sus estudios de grado en el Departamento de Física de la Universidad de Ciencia y Tecnología de China y después un posgrado en el Instituto Hanui, I don't know, the Institute of Optics and Mechanics, Hanui, the pronunciation. Y después se mudó a Estados Unidos, donde realizó su doctorado en la Universidad de Colorado en Boulder, y actualmente es profesor en el Departamento de Física y Astronomía en la Universidad Butler en Indianapolis. Bueno, muchas gracias. Thank you.
Gracias.
Great.
So begin? Yeah. Okay. Buenas tardes. Good afternoon. And today, my talk is on binary stars, Jovian satellites, that's Jupiter's satellites, and asteroids. And next. Okay, so here is the outline of the talk. So we will first start talk about our telescopes, and then we will talk about binary stars, and then talk about the satellites of Jupiter, and then talk about asteroids, and then we will talk a little bit about how you can become an astronomer if you are not, or if when you find a job you are not a professional astronomer, you can still be an amateur astronomer. Next. Yeah, so here is our first telescope in the SARA consortium. SARA is the telescope organization that we share telescopes. Yeah, and we got this telescope free. And here is what happened. This telescope was at Kitt Peak National Observatory at a very good site, a very good view that you can see all around. And then the owner wanted to build a 3.5 meter telescope. This one is 0.9 meter telescope. So they want to build a big telescope, and they want a good location. So they want to, so they dismantled, they take it down, like take this down, and then use the location to build a big telescope. So they have this telescope. They had this telescope in a storage, and they are not going to use it. So they are going to give it to people, and they send letters to universities and ask people that, do you want this telescope free? And if you want, then you write a proposal why it will be useful to you. So 5 universities got together, 5 small universities. So each, the 5 small departments in astronomy, each department is too small and too poor to have their own telescope. So they got together, the 5 universities, the departments of astronomy got together and said, we will put our money together to operate this telescope, so that we will form essentially a big department from 5 universities. So, they started in the southeast region of the United States, like near Florida, that region. So the consortium is called Southeastern Association for Research in Astronomy, so SARA. And so the proposal was very good. So the owner gave the telescope to those 5 universities, and they put the university, they put this telescope here. This is a new location for the telescope. The original location is for another telescope. So that is the first telescope. So next one. Okay, that's an evening view of the telescope. It's very dark. It is about 1 hour west of Tucson, Arizona. It's near the Mexican border. So if you go from here back to Tucson, in the middle of the road, the military has a checkpoint, and sometimes they ask you for ID. I once drove by and they asked me for my ID. Next. So these are our students from Butler University, and we went there and they were having fun. Next. And they made BU here, Butler University, and smile. Next. And that's also a student pointing out where the Milky Way is. This is the Milky Way. The northern hemisphere, the Milky Way is different. And the southern sky is different. In the southern sky, you can see Magellan clouds. From where I am, we cannot see it. I have never seen the Magellan clouds yet. Next. Okay, then a few years later, the owner of this telescope, okay, they only use this telescope about 2 weeks per year, 2 or 3 weeks per year. But to do that, they have to maintain the telescope, make sure it works when they need to use it. So this is very inefficient for them. Yeah. So the owner then asked the SARA consortium, asked them, say, do you want to have this telescope? And the SARA consortium then says, yeah, why not? So So SARA consortium took over this telescope, and the SARA will maintain the telescope, but still give the previous owner 2 weeks a year to use the telescope. So SARA got a free telescope. The other people then still can use it. So everybody wins. And this is very close to here. So this is in Chile, Cerro Tololo. So not too far from here. Much closer here than Indianapolis. So next. Okay, now here is an interesting story. So the big telescope right now is the 10.4 meter GTC, Gran Telescopia Canarias in Observatoria del Roque de los Muchachos. And one of you are there right now. So they have the biggest telescope, and they show this picture to American astronomers, and ask the American astronomers and ask them, say, do you recognize this telescope? And the American astronomers said, yeah, it is the Keck telescope that looks like this. So the European astronomers were very sad. They have the biggest telescope in the world, and yet the American astronomers do not recognize it. So they were very sad, and so they try to make themselves happier. So they thought and then came up with an idea. So next one, the idea is to give this telescope free to Americans. So in this way, then Americans will know Canarias better. So they came to the SARA consortium. SARA consortium is the biggest telescope consortium, biggest in terms of the people. Not the biggest telescope, but the biggest in the people using it. So, they give some condition also. The condition is they will be able to use 10% of this telescope, 10% of the telescope in Chile, and 10% in Kitt Peak. So then SARA says, okay, yeah, we will take it, even though it's only 70% of a telescope. So that's the third telescope we have. So next. Okay, on campus, we also have a telescope. This telescope is 0.95 meters in diameter. The other ones, the one in Canary Islands is 1 meter, and the one at Kitt Peak is 0.9 meters, and the one in Chile is 0.6 meters. So we have a 0.95 meter telescope here. But the thing is, this is in the middle of a big city, Indianapolis, on Butler campus. So it's not as useful as the others. And also the weather here is not very good. It's not a telescope's location, so it's not very good. But when it was constructed in 1954, this was way out in the suburb, so the sky was much darker back then. That was 71 years ago. And when it was built, it was the biggest telescope east of the Mississippi River. Mississippi River is the big river in the US. And it was the 9th largest in the US when it was built. So it was a very big telescope back then. So that's our telescope. Okay, next one. And in the observatory, we also have a planetarium. So, the observatory, it's a fully function, has a classroom, has a telescope, and has a planetarium. And it's a good tourist attraction. So, and it's used for education also. So it's open to a tourist, but it's mainly for education. We charge only $3 or $5. I think it's $3 for children, $5 for adults, and so that's nothing in the U.S. If you take a bus, I think it costs $3. Okay, so why we want to study binary stars? Well, our eyes, the good eyes, without city light pollution, we can see about 6,000 dots in the sky, 6,000 stars, but half of them are actually binary stars or triplets. That is, two stars very close to each other, but because they are too close to each other, we do not see them as two stars. We only see them as one star. And so most stars, or most two-thirds of stars are the doublets or triplets. Our neighbor, Alpha Centauri, our neighbor is a triple system, the three stars together. Two of them are very close, and a third one is a little farther away. And I'm not sure if you read the science fiction three-body problem. That is that's our neighbor. So a lot of stars are binary or triplets. And studying binary stars give us the information about the stars. For example, to get the mass of stars. Okay, if we like to get an experimental value, then you have to have another star, so that if you have two stars going around, then you can use like measure the the period, then you can figure out the gravity between them, so you find the mass. If you just have one star here without anything nearby, then you have no way to measure its mass. But you may say, well, we can derive in theory, like mass determines how bright the star is. But where does the theory come from? Well, the theory comes from the binary stars. So study binary stars are important for developing theories for stars. And yeah, so we can get the information about these stars so that we can have theories. And very important is our telescope is not a very large 1 meter telescope. So the binary stars are just about right for our telescope. If you use the 4 meter telescope to study binary stars, then you are wasting your telescope. And if you have, say, a telescope this big, then it's too small to get enough signal. So our telescope about this big, 1 meter-ish. So that's perfect, a good fit. Next one. Okay, so if you have two objects, like two bodies, so one object here, M1 here, and then M2 here, just like the two stars, or the sun and the earth. Okay, their potential energy is like this. If you feel like put a material into it, it will first start collecting the material here or here. Okay, so next one. And well, L2 is where the James Webb Space Telescope is at right now. So next. So if you add enough material to those two stars, then the two stars could touch. Okay. Next one. Yeah, so here are the situations. So if the two stars are small because the materials are not enough, or if temperature is not enough, then the volumes are small, so they will be inside the so-called Rorschach lobe. And if you have more volume in one star, for example, if you have a red giant, if that blue star turns into a red giant, then it could fill up this part of the potential well completely, so that the material will flow to the other star. And it's also possible that you have a lot of gas, or both stars are red giants. So the two stars are actually merging into one star. Okay, but this is a video, so play the video. Probably push the next button, it will play the video. Oh no. Put the cursor. Okay, yeah. So if one star is blocking the other star, then the brightness will decrease and increase. So here decrease, increase. So one period you have two maximum, one maximum here, one maximum here, and two minimum. So that's how the light curve looks like. And okay. So next. Okay, so here are actual light curves we observe. So those two stars, they are very close. So even under telescope, it's just one star. You cannot see two stars. But the brightness changes because one star is blocking the other one. So that's called eclipsing. So when you have the eclipsing, then you have a minimum and another minimum, and you have the maximum when they are side by side. So side by side, it's depending which side of the star you are seeing. So this side or the other side, they are different. Okay, and the blocking is the same, like one star blocking the other one, or it blocks the other one blocks this star. So based on this information, then you can get a lot of information. Okay, but let's use intuition. Okay, look here, it's not symmetric. If the two stars are totally symmetric, okay, then when it turns around, one side should be the same as the other side. And also this peak here, maximum, should be symmetric. Okay, so, but it's not. It's not, that means the side, this side of the star and the other side of the star are different. So when it's on this side, you are seeing this side, but as it turns, then you are seeing this side of the star. So it's different. So this side has a lower temperature than the other side. So, so using intuition, we can say maybe there is a dark spot here, and maybe there is a bright spot on that side. So that's intuition, but you can write down equation and ask a computer to fit theory to get the exact values. And also, this goes down to this much, this goes down to this much, and that's related to the temperature and the brightness of the two stars. So you get a temperature information. And sometimes you may have a flare. So one flare, these are different wavelengths. Flare is mostly like more observable in the blue than green than red, and infrared almost no flare. Okay, next. So using computer, using equations now, we said one side probably has a hot spot, and the other side has a cool spot. So like one, because of the curve, the maximum one side is the higher than the other side. So that's the result. And also the diameter of the two stars and the distance between the two stars. Next. And here is another binary star. This one is they are actually touching now. And there is a big hot spot. And you can use intuition, say why it's hot, because this star is also hitting this star. If you originally, like, imagine you have a star here, and then you put another hot star next to it. So that makes this part hotter. Next. And the period going around each other. Okay? It does not have to stay constant. It can change. Okay? So in 1 year, it's not going to change too much. But if you observe it over many years, okay, then you can plot out where how the period changes. Okay? It changes just by a little bit. Okay? But you can look at the predicted time versus the observed time of the minimum location in the peak, in the light curve. Okay? When you plot like the difference between the observed value versus the predicted value, then you get a curve like this. This is the time. Okay? This is more than 10 years. Right? So you can see it has some minimum here. So if it has this kind of a curve or the other kind of a curve, it could indicate the period is decreasing or increasing. Okay? one is increasing, the other is decreasing. I forgot which cooling up is increasing or cooling down is increasing. Yeah. So let's observe it over 10 years or so. Okay, if like each epoch is about 8 hours, so divided by 3 is days. So this would be 3,000 days. So that's several years. So total is over 10 years or so. So here, that's over that long time. And then next one, then when we continue observing it, then we see it's not keep going up, it turns down again. So it's doing oscillation. Doing oscillation, then there are two possibilities. One possibility is you have a third body. Okay, suppose like here are the binary star, and you have another body here. They go around, so this binary star going towards you. Okay, if it goes towards you, you may think the period is decreasing because the light takes less time to get to you. But now, by the time it gets to this side and it goes around, then it's going away from you. So you may think, like from the measurement, the period is increasing, and then come back here again. So this could be one possibility that is due to a third body. Okay, and another possibility is you may have some magnetic activities that could change the period. Yeah. So now, and using this, like they both produce more or less the same result. So the 14.5, 13. So that's within experimental value, the experimental errors. You can see the data is not very accurate. So these are the two possibilities. So now the question is, which one is more likely? Yeah. Well, next one. Okay, I already said that. So which one is more likely? So next one. Well, what we can do is we look at the two maxima of the light curve, and the two maxima, the value change. Okay, sometimes one is brighter, sometimes the other is brighter. So the value change, and you subtract them and plot it out. And this maximum change, that's due to the magnetic activity. So, well, when we put the data here, and then it has a period of 5 years. So in other words, if it's due to a magnetic field, magnetic activity, the period should be 5 years. And the result, can you go back to the previous one? So here we have the choice is 14 years or 13 years. So 5 years is quite far away from this. So because of magnetic field, it should be this value. So now we conclude or temporarily conclude that it should be the third body. And the mass of that third body is 0.11 the solar mass. Next, and the next. So, okay, I already said that. And here are additional informations you can get. The mass ratio of the two, and the mass 1 of the star. Like there are two stars, mass 1, 0.7 solar mass, mass 2, about half of solar mass, and the radii of the two, and the luminosity of the two. So, okay. So that's binary stars. And this telescope can also do follow-up observations of other interesting stars. for example, in China, there is a telescope known as a LAMOST. That is a Soviet telescope. It measures the spectra of stars. And it generated a lot of data, a lot of spectra. So some of the stars are interesting, like for example, some active stars, like it has a lot of flares, and it takes a spectrum like this, and well, in theory, from astrophysics, the people conclude that if you have a H alpha transmission, the emission, then the star could be active. And so that's a theory. So now we can check it out, see if that is really true or not. So we picked up this star that has this H alpha, big H alpha, and then we measure its light curve, and here we observed a huge pulse of light, huge flare. And look at the magnitude. So 1.5 here, 0 here, so it's a 1.5 magnitude. So that's 1.5 magnitude is about 4 times, like 400 times as bright as the original. So, so if this happened on our sun, we will not be in good shape. So you have the normal sun, and then suddenly the sun is 4 times as bright, and it threw out a lot of stuff towards the Earth. So that's one thing we do, and here it measures. It lasted for 3 hours. So, so next. And here are some active eclipsing binaries. In like here is the spectra, and here we have the light curve, and this this binary system, you can see the 2 stars are far apart relative to their radius. So that most of the time you see the individual stars added together, and they only block each other for a brief moment. So that's intuition. Okay? So now you can plug it into the computer and calculate exactly how big it is. So next. Okay, so now that's all for binary stars. And here, let's talk about the satellites. Jupiter's satellites. Jupiter's satellites, there is one method to determine its orbit very accurately. And that's when the Jupiter's orbital plane, Jupiter's satellite orbital plane, is parallel to where we are. That happens once every 6 years. That's because the Jupiter's the satellite orbital plane is not exactly the same as the Earth orbital plane. If Jupiter's plane and the Earth's plane around the sun is exactly parallel, then we will see it all the time. But because Jupiter's plane is tilted a little, so when our Earth is somewhere here, then it will be parallel. So that happens once every 6 years. And when that happens, then one satellite can block the view of the other satellite. So 2 satellites normally, but then looking from the Earth, it could block. So once every 6 years, you have this orientation. Other times, it's not on the same plane, so they will not block each other. So, but exactly when it blocks and how much it blocks depends on the exact orbit. So now, and this is a very accurate measurement of the orbit. So using this like to observe it when they eclipse each other, then you can get a very accurate determination of the orbits of Jupiter's satellites. So next one. Okay, I already explained this. So next. Okay, so here is an example. Okay, the actual photo. Do you want to guess what this is? Jupiter, yeah. And these are the satellites. Jupiter has 4 bright satellites. Io or Io, how do you say that in Spanish? Io, Io, then the next one is Europa, I think. And the other ones I forgot. No. Yeah, Callisto and another one. Callisto. Okay. Yeah. So, and here you see like you have 2 there, and then they are getting closer, 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 the overlap, and then they separate again. So, and this happened in, like in a short time. It depends on how well they block each other. Like sometimes the blocking lasted 1 minute, sometimes it lasted 5 minutes, 10 minutes. So that is this part lasts 5 or 10 minutes. So okay. So next. So here are some of the lightcurves. Okay. So like this case, it barely did any blocking, just blocked a little bit. And this one, they blocked each other very well. And sometimes you have 2, and then you ask why there are 2. Okay, 2 is this. Okay, one is it blocks your view, so from the Earth you do not see the other one. But the other case is it blocks the sun. Yeah. So the Earth and the sun are more or less in the same direction. So the 2 events happens not too far apart from each other. So that, do you understand how that works? One is literally one satellite blocks the other one, so you do not see the second one. The other one is it blocks the sunlight, although you can see 2, but the other one is dark. Okay, next. Okay, so now write down equations again and fit your theory to the observed light curve. Okay. And then you can compare the theory with the like the observation. Like this fitting is fitting to the observed data, and compare with the theoretical pure theory calculations. So next. Okay, here are some pictures. That is, if one is blocking the other one, then you lose part of this to reflect sunlight. So next. So here are the results, and here are the important thing. That is how much the brightness change, how much the magnitude change. So, so you need to make this very accurate, the location very accurate. So, so you need to measure its position very accurately. And in the end, the engineers said that we can place the probe, the rocket, they used the upper rocket, waste rocket, recycled rocket, place it 5 kilometers away from the edge. Okay, but remember, like there is always some uncertainty in everything. So they believe that 5 kilometers is far enough to be outside any possibility of colliding. Okay. In the end, it was a few hundred meters, less than 1 kilometer away from the rocket. So, so it was safe, but very close. And so it took a series of photos, and this result was presented much faster, 1 year ahead of the other people, the moon landing people, and got a lot of attention in the asteroid studies. So next. Okay, so to do that, like to determine that location, I was part of the effort. So, so these telescopes, like this one is in Beijing, this is in southeastern China. This one is from the Purple Mountain Observatory, and that's Chile. That's my contribution, and another telescope from Hawaii. So those telescopes were used to observe the asteroid over and over again before it gets there, so that you have a lot of data, so you accumulate enough data so you can determine its trajectory very accurately. And in the end, like it was safe. Next. Okay, now let's talk about the asteroid shapes. So taking a picture, this event was a lucky event. Yeah, that does not cost too much. But if you want to take those pictures like from scratch, it costs like $200 million also to send a spacecraft to take pictures of an asteroid. So you cannot do that too many times. But on the ground, we can use regular telescopes to make observations and get a rough idea of the shape of the asteroid. Okay? And he is a mathematician. He proved it in his thesis that if you have enough data, then you can, from the lightcurve, you can go back to find out the shape of the asteroid. So as a mathematician, he's very famous among asteroid researchers. So next. So here is an example of asteroid 168, and it has this kind of shape. So it's not as nice as a real photograph, but at least you get a rough idea how it looks like. So next. And that's from different directions of the same asteroid. And here is another asteroid. So from different directions. And here are some details to find out where the rotation axis is. And it's using a Monte Carlo simulation. So there is a distribution, but then you get an average where the center is. So this is like to find out where the spin axis is for the asteroid. Next. So here is for amateur astronomers. for a 50-centimeter telescope cost about $35,000. I'm not sure what's the current price. So instead of buy a car, you can buy a telescope. And if you live in a small town, then you can put this in your backyard. So that's the end. Yeah.
Questions? Preguntas?
Thank you, Xianming, for this nice talk. Is this working? Okay. How that you have shown some nice examples of what is called now time domain astronomy. So my question is, how fast is your telescope, or are your telescopes? I mean, how's the biggest time resolution, or the best time resolution you can have with these telescopes for the typical binaries, eclipsing binaries you're observing?
For binary stars, we have sufficient time resolution. Depending on which one, for example, the Chile telescope, the dead time is about the 5 to 10 seconds, like between for the saving the data. And for Kid Peak, it's longer. The camera is slow. But for binary stars, the period being a few hours, so a few seconds is not a problem. But for the Jupiter satellites, because total time is only 5 minutes or so, so you need a good time resolution. So in that case, then you can just save a small part of the picture, so that it will be quicker.
So the limiting factor is the time needed for the camera to transfer the data. Okay.
5 seconds or maybe 6
Okay.
seconds.
Okay. Thank you.
Hi. So you have shown some variation in the period of the binaries in the first examples that you show. Have you studied this, for example, for a sample of objects in order to see if this third star is the most common scenario, or?
Just for that one, or
I'm wondering if you did this for more stars, for just for this one.
just for
Okay. Okay.
When you see a flare, can you distinguish which star is flaring?
yeah.
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 Very basic question. ¿Otra pregunta? ¿En el chat tenemos alguna? No. Bueno, le damos las gracias de nuevo. Thank you.
Gracias.
Sorry for this.
No problem.